Now we are going to start the analysis of heat exchangers. Analysis of heat exchangers means finding out the parameters. There are different parameters in a heat exchanger. For example, the temperatures, the area, and others as well. So there are two methods that are used. One is called the log mean temperature difference method, LMTD, and the other one is called Effectiveness-NTU method or Epsilon NTU method. NTU refers to number of turns units, number of transfer units. LMTD method is used to select a heat exchanger that, or rather, log mean temperature difference method is used. First of all, where did we come across log mean temperature difference term? We came across LMTD while we were discussing internal flow. Right, so there were different temperatures at inlet, and while the fluids were flowing through, the temperatures were getting changed, and there were different temperatures at the exit of the pipe. So therefore, over there we had for the very first time discussed the concept of log mean temperature difference. It is highly recommended that you discuss or you go over that topic again, so as to have a better understanding of log mean temperature difference. So if we know the temperatures, there would be 4 temperatures in principle. Since there are 2 fluids, hot fluid and cold fluid, so hot in, hot out, cold in, cold out. These would be the 4 temperatures. So if we know the temperatures, and if we want to select a heat exchanger, means if we want to work out the area that a heat exchanger will be selected based upon, so that is when we use LMTD method. So LMTD method will be used if we want to find out the size of the heat exchanger, the area in fact of the heat exchanger, and when provided we know the or provided we have the 4 temperatures. And if we have the area, and if we want to work out the temperatures in terms of temperatures, then we make use of Effectiveness-NTU method. Now let's start with the first one, the LMTD method. In fact, what is happening over here is, for example, this is the parallel flow heat exchanger and this is the counter flow heat exchanger. So at inlet, what is the temperature difference? The temperature difference at inlet is Th in minus T cold in. Is Th in minus T cold in. This is the temperature difference between the 2 fluids at the inlet of the heat exchanger. Does it remain same throughout? No. At exit, the cold temperature rises to Tc out, whereas hot temperature reduces to Th out. If you recall the temperature profile of the parallel flow heat exchanger, the temperature of the hot fluid was coming down, whereas the temperature of the cold fluid was going up. So the temperature difference in fact would be maximum at the inlet, and temperature difference would be minimum at the exit of a parallel flow heat exchanger. If I can go back, I will show you that picture again. This is what we were discussing. Yes, this one. So the temperature difference between the hot and the cold fluids would be maximum at the inlet, and the temperature difference between the 2 fluids will keep on decreasing, and it will be minimum at the exit. So the temperature difference is not the same throughout. Temperature difference is in fact not the same throughout. So therefore, just writing delta T will not be sufficient. So we need to have some sort of mean temperature difference, and that mean temperature is taken as log mean temperature difference. Similar things will happen over here. In the case of counter flow heat exchanger, the temperature difference at inlet would be Th in and T cold out, because it is a counter flow heat exchanger. And then at other end it would be T cold in and Th out. Right? So the temperature differences are not keeping the same throughout the length of the heat exchanger. So we need to have a mean temperature difference, and that mean temperature difference that we use is in fact the log mean temperature difference. So the delta T1 and delta T2 expressions in parallel flow and counter flow heat exchanger are being shown over here. Now, so this is in fact the need for the replacement of delta T. Means what delta T would we place? Should we put delta T at inlet? Should we put delta T at midway? Should we put delta T at exit? Because the delta T would have different values at different cross sections. So therefore we need some sort of a mean delta T which is good enough, or which is a good representative of all the delta T's over the entire length of the heat exchanger. So that is why just delta T will not be sufficient. So when we write Q is as MC delta T, mass m dot times C times delta T, this is a very basic expression for Q that we have used in chapter number 8 as well. And over here we can write this product of mass flow and specific heat capacity as CH. So it is CH is simply the product of mass flow rate and specific heat capacity. So we call it heat capacity, because upon it, multiplication with mass flow rate, it will no longer remain specific. So we call it heat capacity. So this has been written in terms of hot fluid, and this one has been written in terms of the cold fluid. So it would be Th in minus Th out. Over here it would be T cold out minus T cold in. Why? Because Th in is greater than Th out, and T cold out would be greater than T cold in, because the cold fluid is getting heated up. So if you recall, or if you go over that material again, instead of writing UA delta T, we do not write just delta T, rather we want to have a delta T which is a good representative of all the delta T's over the entire length of the heat exchanger, which is the log mean temperature difference. We may write it as LMTD, or we may write it as delta T LM. They both mean the same thing. Where what is log mean temperature difference? It is delta T at section 1 and delta T at section 2. 1 and 2 would usually be, it may be any two sections, but it would usually be the inlet and exit sections. So delta T1 minus delta T2 over log of the same, over log of the ratio of the same differences. So what is delta T1? Delta T1 is Th for parallel flow, for example, it would be Th in minus T cold in, whereas and delta T2 would be the delta T at section 2. This is section 1, and this is section 1, and this is section number 2, section 2. At section 2 the difference is delta T would be Th out minus T cold out, but this will not be the same as in, for example, counter flow heat exchanger. At counter flow heat exchanger, at sections 1 and 2, the delta T would be written in, of course, a different form, because of the very obvious and detailed discussion that we had for the last half an hour or so. So it may be written either in this form or in this form, it would not matter, right? Because if we write it as delta T2 minus delta T1, all we need to take care of is that we use the same sequence in the denominator as we have written it in the numerator. For example, if in the numerator we have written it delta T2 minus delta T1, so therefore in the denominator it would be log of delta T2 upon delta T1. So the logarithmic mean temperature difference LMTD is obtained by tracing the actual temperature profile of the fluids along the heat exchanger, and is an exact representation of the average temperature difference between the two fluids. And as I had told you a little earlier, that counter flow heat exchangers are considered to have better performance as compared to parallel flow heat exchangers. So therefore, the log mean temperature difference for counter flow heat exchangers is in fact greater than, it exceeds the log mean temperature difference for parallel flow heat exchangers. Now these are the temperature profiles in case of boiling and condensation. So during the phase change process, one of the fluids temperature will become constant. For example, in case of condensation, one fluid will be getting condensed, so the heat would be coming out of it. So the condensing fluid would be termed as the hot fluid, and since the heat is coming out of it, that of course heat will be given away to another fluid which would be at a lower temperature than the condensing fluid. So since it would be at a lower temperature than the condensing fluid, we will call it as cold fluid. So the temperature of the condensing fluid will remain constant, whereas the temperature of the other fluid, which would be the cold one, will increase. Similarly, in the case of boiling, one fluid will be boiled. Its temperature will become constant. So it will be converted into vapor state, for which it requires energy. Since it requires energy, so therefore the energy would be given by another medium which would be at a higher temperature than the boiling fluid. So therefore the boiling fluid would be the cold fluid in this case, and the other fluid which is at a temperature higher than the boiling fluid will be termed as the hot fluid. So the temperature of the hot fluid, for example, in the case of boiler, the hot fluid would be the combustion gases. So the temperature of the combustion gases would be more than the fluid, which is more than the water, which is under phase change process. So therefore the temperature of the combustion gases will continuously go down, whereas the temperature of water or the boiling fluid will remain constant. So the temperature profiles of both the fluids may change, whereas temperature profile of one of the fluids may remain constant in the case of phase change process. Now when we come to a multipass or a cross flow heat exchanger, see, the thing is that when we talk about cross flow heat exchanger, it is neither parallel nor counter. Similarly, when we talk about multipass, a certain portion of multipass would be parallel and a certain portion of multipass would be counter. So in those cases where it is neither completely parallel nor completely counter flow heat exchanger, we then use a correction factor. A correction factor in finding out the log mean temperature difference. So the log mean temperature difference, which we had discussed earlier, is limited to parallel and counter flow heat exchangers only. Is limited to parallel and counter flow heat exchangers only. And there are some relations that are for cross flow and multi pass flows as well, but they are too complicated to use at this level. So what the scientists have found out is the use of this expression, which says that the LMTD for cross flow heat exchanger or for multipass flow would be found out by multiplying the LMTD for counter flow with a correction factor. And this correction factor will have a value of 1 for counter flow heat exchanger, otherwise it would be less than 1. It would have a value of 1 if it is a counter flow heat exchanger, otherwise it would be less than 1. And in fact this correction factor, as is very well defined over here, is a measure of deviation of the log mean temperature difference from the corresponding values for the counter flow heat exchanger case. So it takes into account the deviation. The smaller the correction factor is, there would be more deviation of the LMTD for cross flow or multipass heat exchanger from counter flow heat exchanger. Now how do we find out correction factor? We have those diagrams which are mentioned over here. I have taken those diagrams from Yunus Singhal. Over here there are various such diagrams. For example, this one is for 1 shell pass and 2, 4, 6 or any other multiple of 2 tube passes. The second one is for 2 shell passes and 4, 8, 12 or any multiple of 4 tube passes. And we have two more. For example, single pass cross flow with both fluids unmixed and single pass cross flow with one fluid mixed and the other unmixed. So let's discuss those first. So on the x-axis is a certain parameter which is P, which will be found out using T2 minus T1 over T1 minus T1. So there are small t's and large t's as well. Now what are those small t's and large t's? As per this diagram which has been provided over here, small t refers to the temperatures of the tube side fluid. So small t1 would be the temperature of the fluid which flows through the tube, and T2 would be the temperature of the fluid which comes out of the tube. Similarly, capital T refers to the temperatures of the shell side fluid. So T1 would be the temperature would be the inlet temperature of the fluid which enters the shell, and similarly T2 is its outlet temperature. So we will find out P using this expression, and we will find out R using this expression, T1 minus T2 over T2 minus T1, and then we will join them together. These are the lines for R, curves for R, and on x-axis we have got the values of P. So we will intersect, and from the y-axis we will read out the value of the correction factor. So this is how we would be finding out the correction factor if it is the case of multipass heat exchanger or cross flow heat exchanger. Similarly, for 2 shell passes and 4, 8, 12 etc. or any multiple of 4 tube passes, this one was for 1 shell pass, and this figure B is for 2 shell passes. We will do the same thing. Over here are mentioned all the temperatures, and we will again be finding out P and R, and we will be reading out correction factor from y-axis, from ordinate. Now moving forward, the correction factor for single pass cross flow with both fluids unmixed, and over here we have got single pass cross flow with one fluid mixed and the other unmixed. So we can see over here that both the fluids which are unmixed have been shown in this way. So of course T1 would be and T2 would be the inlet and exit temperature of one fluid, and capital T1, capital T2 would be the inlet and exit temperatures of the other fluid. And over here small t refers to the temperature of inlet and exit temperatures. Small t1 and small t2 refer to the inlet and exit temperatures of the fluid which is unmixed, because its direction has been fixed. Whereas capital T1 and capital T2 refer to the temperatures of inlet and exit temperatures of the fluid which is which is mixed, because this does not have that particular pattern. So we will at the end be reading out the correction factor from the y-axis. So in the end, this is a very useful discussion which has been presented over here. As I had mentioned earlier, that log mean temperature difference, since it requires the calculation of log mean temperature difference, so therefore we must know all the 4 temperatures: hot in, hot out, cold in, cold out. So this method will be used when we know the inlet and exit temperatures of both the fluids, and the job is to find out the heat transfer surface area, means the sizing of the heat exchanger, means when we need to select the heat exchanger. So this is when LMTD will be used. So therefore the LMTD method is very suitable for determining the size or the area of a heat exchanger. Now with this method, the task is to select a heat exchanger that will either meet or exceed the prescribed heat transfer requirements. So the area so the area of the heat exchanger which is available out there in the market should at least be the same or exceed the area as per our calculations. It should be as close to the calculated value as possible, however. So the procedure is as mentioned over here. Select the type of the heat exchanger suitable for the application, means shell and tube, 1 pass, 2 pass. We need to determine the number of passes, or spiral heat exchanger, or plate heat exchanger, or whatever kind of heat exchanger it is. Determine any unknown inlet or outlet temperatures. So this must be known. We must know all the inlet and outlet temperatures. Calculate log mean temperature difference and correction factor if necessary, means if it is a multipass heat exchanger or if it is a cross flow heat exchanger, then we also need to calculate correction factor. If it is a parallel flow heat exchanger or counter flow heat exchanger, then we do not need to calculate correction factor. Then obtain, means select or calculate overall heat transfer coefficient, and then using Q is equal to UA LMTD, calculate the surface area. Now the next or the second method for heat exchanger analysis is Effectiveness-NTU, and this method will be used if the outlet temperatures are not known. So a second kind of problem encountered in heat exchanger analysis is the determination of heat transfer rate and outlet temperatures when the type and size of heat exchanger have already been specified. So we would know the size of the heat exchanger, means the area would be known, and if we want to find out that what would be, means that we would be knowing that the type and size of the heat exchanger. And if we want to find out that if this heat exchanger is used, then what would be the outlet temperatures of the hot and the cold fluids, then we would be using the Effectiveness-NTU method. Although the LMTD method can also be used, but it would require extensive iterations for that. So therefore it is better to use Effectiveness-NTU method. What is effectiveness? First of all, it is a ratio of Q to Q max, where Q is the actual heat transfer rate which is taking place, whereas Q max is the maximum possible heat transfer rate. Now when we talk about the actual heat transfer rate, actual heat transfer rate can be found out by MC delta T, either for the hot fluid or the cold fluid, and we have seen those equations on one of the previous pages. This one has been written in terms of the hot fluid, and this one has been written in terms of the cold fluid. Now maximum heat transfer rate will be given in this form, where we would be requiring maximum delta T, and maximum delta T would be between hot inlet temperature of the hot fluid which is coming in, and the temperature of the cold fluid which is coming in, because this would be the maximum temperature out of the four temperatures, Th in, and T cold in would be the minimum temperature out of the four temperatures. So therefore we will write it as Thi minus Tci. Therefore epsilon effectiveness can be written either in the form of this expression or in the form of this expression. Only the numerators have been written once for with respect to the hot fluid, and once for with respect to the cold one. And then we can write this expression from here as well, or rather from here, because the numerator is in fact Q. So therefore Q is epsilon times C times Thi minus Tci. We also have a parameter over here which is a representative of the size of the heat exchanger, means the area. We call it number of transfer units, NTU, and NTU is given as UA over C min, where U is the overall heat transfer coefficient and A is the, of course, the surface area of heat transfer, and C is the product of mass flow times specific heat capacity. And then capacity ratio is the ratio of the C min over C max. Of course, mass flow times specific heat capacity for the two fluids would be different if the fluids are different, having with different mass flow rates. So then one of the product would be having a lesser value and the other product would be having a larger value. So therefore the one having the lesser value will be called C min, and the one having the larger value will be called as C max. We are not going into the derivations, rather we will be looking at the expressions which will be used. It is table 11.3 of our book, and over here in this particular table are listed the relations for effectiveness. For example, if it is a parallel flow heat exchanger, then effectiveness will be can be written in this form, in this expression, whereas in counterflow it may be written in using this particular expression. And if it is a shell tube with one shell pass or n shell passes, or if it is a cross flow with both fluid mix, one unmixed, C min unmixed, C max unmixed, and the other one mixed, so then these are all the expressions that are provided over here in this particular table. Of course, you do not need to learn them by heart. If any problem appears, of course the expressions would be provided, just like you will also be provided with the expression of Nusselt number at the end of chapters 7 and 8. Now this is almost the same table as the last table. Over here, over there we were given epsilon effectiveness, and whereas over here we are given the expressions of NTU. Of course, they have been taken from here, of course. So if we take log on both sides and then work the things out, and we would be able to take this NTU on the left hand side. So then we would be getting those expressions of NTU. However, we really do not need to use any of those expressions. Rather, those expressions have been translated into some easy to use graphs or charts. So if, for example, we have a parallel flow heat exchanger, so then and if we know NTU or this ratio, then we can find out the effectiveness. Or if we know the effectiveness and this ratio, C min over C max, then we can find out NTU. So we really do not need to make use of those expressions. Rather, these easy to use graphs can be made use of. So the first one is for figure 11.10 is for a parallel flow heat exchanger. Similarly, the second one, 11.11 figure, is for a counter flow heat exchanger, and this one is for shell and tube heat exchanger with one shell and any multiple of two tube passes. This one. So over here we have got this THI or TCI or TH naught or TC naught, because it may be the hot fluid which may be on the shell side, or it may be the cold fluid which may be on the shell side. Similarly, the hot or either hot or the cold fluid can flow through the tubes. So it would depend upon the case. So if this is the case, means if we have a single shell pass and multiple of 2 tube passes, 2, 4, 6, 8, 10, then we would be able to use this graph. And if we have 2 shell passes and any multiple of 4 tube passes, then we would be able to use this graph. 2 shells have been made over here, and of course the ones that are shown over here are 4 tube passes, but it can be 4 or 8 or 12. This figure, or rather these figures, are for cross flow heat exchangers, and by looking at this diagram we can see that both fluids are unmixed, and with this is what is mentioned over here, with both fluids unmixed. And over here one fluid is unmixed, this direction, and the other fluid is mixed. So in this case, if this is the case where it is a cross flow heat exchanger and one fluid is mixed and the other unmixed, then we would be using this particular graph. So in the end, in fact, the selection of heat exchangers depends upon various parameters. Of course, heat transfer rate is a very important and major factor. Of course, because we must be able to get the required heat transfer from the heat exchanger that is being selected. And its cost plays a very important role, because in any business we need to know the B by C analysis, benefit to cost analysis, or the payback period, or other financial parameters. The pumping power is an important point, because the fluid will be made to flow through the tubes and through the shell. So therefore there would certainly be a requirement of pumping power of the fluids. Size and weight would matter. If there are space constraints, we will go for multiple passes. Okay? And of course material would be based upon selection of material. Type would also be there, means shell and tube or plate heat exchanger or spiral heat exchanger. Selection of material would be based upon the maximum temperature that will occur in the heat exchanger. Of course, the higher the THN is, the material requirement will become tougher and tougher, and there may be other considerations as well. In fact, there is Tubular Exchangers Manufacturers Association TIMA classification is there. I will try to upload something on TIMA so that you can take a look at various classifications of TIMA as far as the heat exchanger selection is concerned. These are few numericals that we will be taking over one by one. These are all the four are from our book. So that is all about the material of heat exchanger. And now we will start solving problems with using the two methods, of course, the log mean temperature difference method and the Effectiveness-NTU method, so as to see that how they can be applied in real circumstances.